using 30 times too much power.
This is saying right now that we're actually producing more CO2 than we're taking out.
Yeah.
I don't want to scale something up that we don't have operating at an optimal efficiency. I'd like to try and troubleshoot some of these problems before we try and scale something up.
If this prototype caustic soda tower system were deployed on a global scale, it would accelerate climate change, not slow it down.
The challenge that we have is basically making the efficiency of the entire system work, and I'm extremely concerned that we're not going to be able to achieve that efficiency.
Jennifer and Frank will continue working on the problem. But even if they can find a way to efficiently remove CO2 from the air, they face a major problem. Where do you safely store billions of tons of carbon dioxide? It turns out nature already has the answer. It's called weathering. Rain wearing away at minerals can trap carbon dioxide permanently through a common chemical reaction. But it's a very slow process. Now, Dr. Andrew Chismesha wants to use extreme temperature and pressure to accelerate the weathering reaction 1 million times and lock carbon dioxide in rock. To see if the process works, he needs an X-ray machine 1 million times more powerful than those used in hospitals. So he's at the synchrotron at the Argonne National Laboratory near Chicago. It's so vast, scientists use bicycles to get around inside. Basil has come here to meet Dr. Chismesha and test his theory.
These are the minerals that we're talking about.
Dr. Chismesha's plan is to react carbon dioxide with a mineral called serpentine. This will transform the serpentine into a new mineral, with CO2 locked inside it. It's the same way weathering works in nature. To do this, he has to pressurize the mineral and heat it to nearly 540 degrees Celsius. He believes the right combination of temperature and pressure will make the reaction almost instantaneous. They just have to find that combination. No one has ever managed to do it.
What we're trying to do is really delve in and get a microscope and really look very finely into exactly what's going on a very small chemical scale. And once you know the fundamentals of the science and that it works, then you expand on that and industrialize it.
So before this mineral can be used in our process, we have to grind it. And then we take this powder, which we insert into our microreaction chamber. We add the water, we add the CO2, and we fish for the reaction.
To get the mineral in the path of the powerful X-rays, the whole experiment has to be done in this tiny glass chamber. It's pressurized with carbon dioxide to 140 times atmospheric pressure. With the X-rays powered up, the experiment begins. Gradually, they increase the temperature. They're looking for a spike on this graph, the chemical signature created when the CO2 is trapped. The temperature's increased a little more as they search for just the right level that will maximize the chemical reaction.
Now, we can take a critical CO2. This is now.
Under the ideal combination of pressure and temperature, the reaction should be almost instantaneous.
Oh, there we go.
There goes.
What peaks
All right,
have we got?
well, we have some magnesite.
Yeah?
There we are. There it is.
So we're properly taking that CO2 and converting it into a
form.
mineral.
Yeah.
It's never going to come back into
Right.
gas.
It'll never revert back, yeah. It's a very stable mineral carbonate form. Thank you.
They've transformed the serpentine into a new mineral called magnesite by locking carbon dioxide inside it.
The experiment went very well. We actually showed that we can convert CO2 gas into a mineral, into a permanent carbonate mineral.
Right now, it's just a lab experiment, but the basic science works, and that's a huge leap forward. Locking CO2 in rock may work in the long term, but Basil has to find a more immediate solution. That's why he's come to southern France.
I'm here to see a company who specialize in fluid dynamics. One way of disposing of CO2 is to freeze it down into dry ice and send it down to the bottom of the ocean.
In the late 1970s, an international team of scientists conducted experiments to see if torpedoes filled with nuclear waste could bury themselves beneath the ocean floor to safely store radioactive material. But the technique was never put into practice. Basil wants to know if these torpedoes could be redesigned for CO2 disposal. Dr. Nick Murray, a member of the original French team, has been working on the idea.
Very nice to meet you. Thank you very much. Okay, I'll try and explain to you what the basic idea is. We have a penetrator. This is a little Model 1 you see here. And the tail fins here, which is that, are made out of very light aluminium so that they control the descent of the penetrator through the water column.
Yeah.
In the middle, we have the blocks of carbon dioxide.
The concept is elegant. Turn captured CO2 into the body of a deep-diving torpedo. To do this, they have to first freeze the carbon dioxide into dry ice. Then the dry ice is cut into cylinders.
That's just over 2 pounds of solid CO2.
The cylinders are threaded onto a steel bar. Finally, Nick fits a heavy nose and a fin tail onto the dry ice stack, completing the prototype torpedo. The torpedoes will be dropped from a ship. Carbon dioxide will begin to boil off, but will stop as the torpedo descends and the water pressure increases. The torpedo should then bury itself in the seafloor sediment, in theory trapping the CO2 forever.
That's pretty cool, isn't it? I want to go and have a look from down there.
For the launch to be successful, the torpedo needs to strike the ocean floor nose first. But Nick and Basil worried that the CO2 bubbles could throw it off course.
The real test is going to be tomorrow out at sea, and the big unknown is, will these torpedoes embed themselves into the sea floor? I've got no idea if this is going to work.
Early the next morning, Basil heads into the Mediterranean Sea on a research vessel to test the torpedo.
This is the first time that anything like this has ever been attempted, and I haven't got a clue how it's going to pan out. For a start, CO2 is really brittle stuff, and it's quite fragile, and in such large quantities it could easily just crack up and disintegrate. Also, when it goes into the water, no one's really studied how the CO2 bubbling off the structure is going to affect its trajectory through the water. We want it to go straight down, and I hope it does, but we don't know.
The ship comes to a stop in 760 meters of water. It's time to assemble the dry ice torpedoes.
As soon as we open these boxes, this dry ice is going to start melting away, so we've really got to get on with it.
Dry ice changes directly from a solid to a gas. Every minute the frozen CO2 sits on deck, 3 grams of it escapes into the atmosphere. At T-2, depth sensors in the torpedo are on, and a video team is in the water.
Okay, guys. Has it been calibrated?
Yes.
Yeah?
Yes.
Fantastic. Oh. All right, guys.
Si on peut ramener un peu le portique par là. On peut avancer un peu le...
On this torpedo, it's about 70 pounds worth of frozen CO2, which is equivalent to the emissions